I'm Saverio from the University of Bologna, and I'm a member of the area OLAS team. And this is joint work with Marco Peressotti and Fabrizio Montesi from the University of Southern Denmark. And we split the presentation both because we are both here, but because one introduces choreographic programming, since this is, we think, the first time choreographic programming goes mainstream. So we introduce choreographic programming here, then of course all of you will know it and nobody needs to introduce that anymore. And then we will talk, of course, about Choral. I will leave the floor to Marco. So let's start from the context where choreographic programming was born, that of concurrent and distributed systems. And programming correctly distributed systems is hard, distributed and concurrent systems. And the problem is we have in mind a specification, and usually we use these kind of schemas to represent those. So you have, let's see if this works, you have participants that are also called roles in choreographies, and then they exchange messages. So they interact through messages and they exchange data. And it's simple to see what happens in this protocol. We have C sending some credentials and then a branching behavior that is distributed where A checks the validity of the credentials and then sends OK or a KO to WS, which sends either a valid token or an empty one. So it's pretty straightforward to see what happens. But then if you look at the implementation there on the right, you see that it's not so easy to check that the implementation is actually doing what the specification does. And if I hid the specification, it would be probably even harder to understand what happens in the distributed system just by looking at the single endpoints. They are also called the implementations separated. So, and we know that even debugging the stuff and finding, so making sure that we correctly implemented the protocol and debugging the implementation, finding the bugs due to concurrency is difficult due to non-determinism, right, and the state explosion problem. So the idea of choreographic programming is we have already the schematics. Why don't we start from there and then let a compiler do the job of implementing correctly the distributed system? So what we do is that we give a artifact that is closer to a programming language to the programmers so that they can express the local computations, the general transitions in the system, the interactions in the system. So you have something like this where you can say, I have a role, C that has some value. This value is stored under the variable credential, which is local to C, and then an interaction that transmits that information to A, which stores that information under X. So given this information, we can compile the general schematics into the implementation in a correct way, meaning that we have theorems saying whatever the choreography says, the implementation does, and the implementation cannot do more than what the choreography says. And this is what we normally call the choreography compliance guarantee. So we don't have surprises. And the corollaries are really communication safety, so there is nothing unexpected by one of the members done by some other participants. And we don't have deadlocks on messages. And this is simply because we have this interaction that says this is a send and a reception that are always paired. So you can never write syntactically a send that is unmatched by a reception. So the foundations are pretty much there. It's been, let's say, 12, 15 years we've been working on the paradigm. So the question we asked with Choral is this paradigm ready so that we can bring it to the mainstream? And to answer this question, we wondered if we could merge a mainstream modular way of building software in the large to choreographic programming. And the idea with Choral was, okay, let's try to do that with object orientation. It's widespread, it's working, so why not using that? And by marrying choreographic programming with object orientation, we actually found that we have new understandings of what is abstraction, encapsulation, polymorphisms, because we are elevating those at the level of choreography, so at the level of the distributed system. And the additional interesting point is, and that was explicit, of course, we modeled Choral as close as possible to Java so that it feels like Java and you can interact with Java programming. You can import Java libraries in Choral and bring them up to the choreographic level, but you can also have, and this is the next slide, you can also have classes that are at the choreographic level that you can compile down to Java classes and you can use in your local code. So that now you have local code that can take part in a choreography and in other choreographies too. So you have this double interpretation. And then I can leave the floor to Marco for more on Choral.
Thanks. So how we came up with the design of Choral. The first thing we needed to do was essentially looking at the primitive for communication, that is the core of choreographic programming, and interpret it or understand what would be its equivalent in object-oriented programming. Here we see on the left what has been happening traditionally in choreographic programming until Choral. And communication is expressed with this arrow primitive. It means process P evaluates an expression E, sends the result to Q, that will store it under variable X. This is a primitive of the language, it's a statement, and syntactically combine the sending and receiving, as Saverio said. When moving to an object-oriented setting, we instead moved from a primitive to a method invocation, and we leverage the properties of object orientation in order to avoid fixing an implementation. This is no longer a primitive, it's just a method invocation. It's one of the main objectives we had with Choral. We wanted to avoid fixing and committing on a middleware. The other main difference is that in the traditionally, the placement of data and placement of computation, for instance, evaluating this expression, has been made manifest at the level of syntax with these prefixes. You needed to annotate every single variable, piece of data, and etc. Instead, with Choral, we leverage the rich type system of the object-oriented language in order to express this property. This allows to get a syntax that is a little bit more similar to essentially programming in Java. Thanks to this new type system that allows to track data placement. For instance, here we have this expression is meaning that we have an integer that is located at A, so a process or a participant A. Thanks to this interpretation, then communication or a channel could be any object that has a method that allows to take data located at A and returns data of the same local type located at B, like anything with a signature like this one, for instance. Then we expect from the realization of this in the local code, so the endpoints, to have essentially two objects that offer a method with these signatures. So for the sender, for A, we expect to be able to provide an integer or the payload of the message, get nothing out of it. On the other side, we want to just get the result. So essentially a send and a receive. Now, this means that this kind of method needs to be offered by an object or a type that is distributed across two roles, A and B, but they are combined in a single artifact. Then when we compile it, we will get, again, a definition for the sender, a definition for the receiver. But what is important for us is this is just an ordinary interface in Choral. It's not a primitive, there's nothing special about it. And this means we don't need to commit on any specific implementation. In the standard library of Choral, we have some default implementation, leveraging, I don't know, TLS channels, various methods of serialization. You will find many examples in the paper and on the website. It also allows us to leverage the object-oriented principles of encapsulation, polymorphism, subtyping. We have a hierarchy of these interfaces that allows you to express different capabilities. I want to have a bidirectional channel, there is an interface for that. I want to have, I don't know, a broadcasting channel, there is an interface for that. And allows you to decouple, again, specifying what are your capabilities and what are the implementation details. Now, interesting thing is that now we have these types that can be distributed. They can talk about multiple roles and participants. And here is an example to give you a taste of Choral. It's a replicated cell. So we have this class, and I will walk you through the details while we compile it. we have this class distributed across two participants, Alice and Bob. And here on the right, we have the implementation for Alice. So we just get a simple class for Alice. We're using the underscore for the role. And then here we will have Alice as a private field of an integer located at Alice, so that will be projected to a field for Alice. Bob has an equivalent field, will not be see anything for Alice. They share a channel in order to share updates to these replicated data. And for that, they have a specific channel. Then methods. Here we have an example, a method for that allows Alice to update its value at this line, and then communicating the value to Bob that will update its field. Again, this will become just a send for Alice and symmetrically a receive for Bob. The interesting thing here is that the design of Choral allows you to control the API. Here, by looking at the API at the choreographic level, you can already understand what the API for the implemented code will look like. And here we have the symmetric case. So we ran some evaluation in the paper. This was a simple example. There are more in the papers running from the choreographic equivalent of Hello World, with just a couple of lines of code, to more complicated distributed authentication protocols with, I don't know, 10, 5 participants. And what is, for us, the most interesting metric is how much code we can save. So we run from a gain of 55% in terms of size increase to almost 400%. This is code that compiler is generating for us. We avoid much of these exponential explosion in terms of possible combinations we don't need to check. We also made another evaluation doing an architectural refactoring. We started from an existing application, an open source microblogging platform based on Java service pages and Redis. And we wanted to create a distributed version, essentially moving from a monolith implementation to a microservice. We use Choral for programming the interaction. Everything else, logic, data structure, etc., we lifted from the existing code, Java code. And what we gained was essentially a drop-in replacement. It was not so complicated to get essentially to a distributed implementation. There is way more in the paper, but essentially what we achieved is a language for programming distributed system that brought modularity and object orientation to choreographic programming, moving it beyond just the community of concurrency theory. Is fully interoperable with a mainstream language, Java. And in the paper, you will find that the compilation is fully specified. There are more details for the evaluation. For instance, we did a comparison with Akka and Java. And you will find more details about the development methodology. What should go in the choreography, what should stay in choreographic code, especially for error handling. And since now we have this dimension of choreographic code, we also started wondering, how do we test this distributed system? We have a way of specifying tests from a global perspective of our choreographies. And so we had a kind of choreographic JUnit, if you want. And the other thing I want to point out is that the first release of Choral happened in 2020. Since then, we've seen that many of the ideas developed with Choral started popping up in other languages. There has been work on Haskell by Lindsay team. There has been, I think, 2 already implementation bringing these ideas to Rust. So this sparkled kind of an explosion, bringing choreographic programming to the PL community. So thank you, everybody, for your attention.
Thank you very much. We have lots of time for questions. If anyone would like to head to the mic, and we even have a mic now. Thank you very much. Just in time, mic placement.
Okay, thank you very much for the nice talk. Can you hear me, actually? Maybe I have to do it this way. That's. I have one question, and suppose you have 2 channels, and they share either the sending side or the receiving side.
Yeah.
What's going to happen?
Well, depends on the implementation of the channel. But if there is any interference, like, I don't know, you have 2 objects that represent 2 channels, but you're sharing a socket, then the compiler cannot give you any guarantee there. So instantiating the choreographies and setting up the channels is, in a way, outside of the language. But the moment you can have multiple channels between the same participants. So for us, it's just an object there. I could have, I don't know, 3 channels between Alice and Bob because one is encrypted, the other one is in clear.
No, I mean 2 channels that really have the same endpoint or the same starting point. Do you rule this out? Do you have a compiler check for this?
So like one sender and 2 different receivers?
Yeah.
No, it's possible and it's not an issue.
What do you do then? Broadcast?
Sorry?
Do you broadcast then?
No, there are 2 separate channels with their own implementation.
Okay.
Yeah,
Okay.
but we have examples in the library of channels for broadcasting, but in that case, they are specified as an object that involves a sender and, I don't know, 5 receivers. How many?
I meant rather if you write it like this.
Yeah.
But I think we should probably take it offline.
Okay.
Thank you for the talk. Very interesting. I was wondering about error handling and exceptions. Yeah, like because if you throw an exception and it's something that's getting compiled to 2 different files into different machines, so how do you approach error handling?
That's a super interesting question because, I mean, in general, error handling, I think, is not a solved problem for choreographic programming in general. There is a lot of active research there. We are still brainstorming about what could be a good solution. Choral has an exception mechanism, but those are local exceptions. So for that, much of the work relies on the programmer. So up to the point these are local exceptions, they can be handled, but we don't have a mechanism for distributed exceptions because we don't assume a middleware. Of course, one could have rely on some libraries in order to coordinate this. And for instance, if you work on the theoretical works on choreographic programming, multi-party session types, the moment they start dealing with exceptions or user-generated errors, they assume some form of reliable communication in order to handle coordination. What we discuss in the paper, especially in relation to the development methodology, is if errors or exceptions are part of the protocol, then they need to be handled at the choreographic level. If these are, let's say, non-recoverable exceptions from the perspective of the protocol, then at the moment, these are just going to pop up to the caller, to the invoker of the choreography, and at that point, we are out of what we can handle at the moment.
Thank you.
We have time for one more, I think.
Very energetic talk, thank you. My name is Krishna Nandioda from IIT Madras. I had a question related to the programmer's view of this. Typically, we like to, for large applications, independent parts separately, because it's easy to write the code, easy to maintain the code. And now you are proposing, hey, let's mash up everything together, right? Your thoughts on that? Thank you.
Not everything, but the communication part. So the idea, also the origin of the name is Choreographies as a library. That's the AL. Usually, I mean, you can program an entire application in Choral. I'm not going to stop you. But especially in order to maintain this modularity of code and et cetera, the idea would be you use the choreographic language, the choreographic level, to program the interactions. But for the local logics of your endpoints, that you rely on your language or technology that you prefer. Because then, I mean, it's how many things happen. You just release the communication library, like giving an endpoint client in order to access your cloud API. So this is more or less what we suggest.
We can squeeze in one more question while the next speaker sets up.
Okay, yeah, thank you for the interesting talk. Just a quick thing. I think it's related to a couple of the other questions, and that is, as I see it, the main sort of design contribution that you made was to abstract over the communication, the implementation of the communication protocol, right? So have you thought about what correctness requirements that communication has to satisfy? You know, like if I go and implement my own communication primitives for some particular platform, implementation platform, what are the requirements that my implementation has to satisfy?
Okay. So right now, for the channels you will find in the standard library of Choral, the assumption is essentially this is a reliable channel, which is a high asking. Under that very high assumption, then this is data free, everything works, of course. There are libraries offered with Choral, and Dan Plugin worked on one of those that offer you a different channel API that allows you to handle errors, program asynchronously on channels, and then, of course, I mean, it depends on the kind of implementation you want to pick. And the compiler is, I mean, you don't even need to touch the compiler. You just need to plug in the library of your choosing.
Great. In 1 second, we're going to thank our speaker again. I'm going to suggest that because there's an accumulation of people near the door, there's lots of seats over this side. So if you want to come around the front and just fill up those seats, and we'll applaud our speakers again. Thank you very much.
Thanks. Cool.